continuing along here and picking up with this section on the uncertainty principle, which is a really famous part of quantum mechanics. You're probably familiar with Heisenberg, the Heisenberg uncertainty principle. And so we're going to build up that discussion using these generic examples, okay? But as we progress through the course, we will see actual physical implications of the uncertainty principle, okay? So I'm first going to start with our generic wave function, psi equals ae ikx plus be minus ikx. And I'll remind you, we got this wave function from solving the one-dimensional time-independent Schrodinger equation. So it's kind of accurate, but not completely, because it's only one dimension, right? And so also recall when we were talking about operators, we played this game of operating on psi with the momentum operator. And we played this game by saying, well, let's call b equals 0 and see what the result is. And then let's call a equals 0 and see what the result is. And so I'll remind you, when we said b is equal to 0 and the momentum operator operates on the wave function, we get back the original wave function plus the eigenvalue. And so that eigenvalue very much represents the momentum of the particle. And so recall k is that wave number solution. So it's like the 2me divided by h bar all square root, all right? So, but we'll just represent that as a constant for now, okay? And so also recall when a is equal to 0, we got this negative k times h bar, okay? And so there's a couple consequences of this, all right? And so if we now start thinking of this momentum state as a property of particles, okay? So in other words, I've got a particle flying through. It has mass and it has velocity, therefore it has momentum. We want to know now, how does that particle property translate to a wave property, okay? So I can think of that now as some total wave function being psi plus and psi minus related to each of these two terms, okay? And in the case for psi plus, we could view that so as a particle with momentum positive kh bar, and that means in this 1D scale, this would be a particle traveling in this direction, okay? And so recall that also came from our discussion of the second derivative giving us this idea of curvature and kinetic energy. So as you can see here, the kinetic energy is very low, and it picks up and it picks up and it picks up, and it really increases going up this curve, okay? Well, we also have this negative momentum state given by negative kh bar, okay? And we could view that as a particle moving to the left in our 1D Cartesian coordinate scheme, okay? And so what we have going on here now is, what this implies, the physical implication of this is, in a large number of measurements, there will be an equal probability of finding particles moving to the left with this negative kh bar momentum state, and particles moving to the right with this positive kh bar momentum state, okay? And so then the idea, what we would see is we'd find the most probable value to be somewhere right there, okay? So what we call this, when we see this very sharp wave function giving us a peak, we call that a wave packet. And that's this idea of this confluence of wave properties and particle properties converging to this singular point of where we might find the particle. It's the wave packet, okay? So another amplification of this is a wave function is a superposition of more than one wave function. So in this simple example, we might see this as a superposition of two wave functions, one describing a particle moving to the right, one describing a particle moving to the left. Okay? And as we build up more and more of those wave functions, like it says up here, we would find an equal probability of particles moving left, particles moving right, owing to this being the most probable position. Okay? Let me erase that terrible looking arrow. Okay. So what we need is a linear combination of wave functions. And by linear combination, we just mean psi plus, plus psi minus, et cetera, et cetera. And we call this the basis set. And this basis set will describe a particle's physical properties with as much accuracy and precision as possible. And really, precision here is the key, because the more narrow that peak gets, the more precise we get. Okay? And so if we look at this, so now this is a figure from your mathematics assignment that you're working on. We call this the superposition. Okay? And so recall, I was playing with this in our Friday discussion the other day, right? When we look at n is equal to 1, you can see we've got a fair amount of uncertainty. Let me change the color. We have a fair amount of uncertainty in the particle's position with this n equals 1, because we've only put in one momentum state. Okay? But now, as we add more of these momentum states, okay, we're building up our superposition, and the uncertainty gets smaller and smaller and smaller. Okay? And so I won't continue on drawing the colored arrows, but you can see where this is going, right? As we add more and more of these, we become more and more certain of the position. And I'll just demonstrate for you. I've got that down here. So on this graph, I'm just showing you psi, which means we're going to have positive and negative values. Okay. Over here, I've got it as psi squared. So this is the same wave function to describe this idea of the superposition. And if I add two superpositions, or two wave functions in my basis set, then as you can see, I'm getting this constructive and destructive interference that gives me more certainty in the particle's position. And as I keep adding more and more terms in my basis set, right? So here, basically, my basis set, right, is this sum of individual wave functions with, of course, their corresponding normalization constants, which in this case now these normalization constants become weighting factors, right? So in other words, if there was only two of these, it would be 50-50. With three of these, 33%, 33%, and 33%, and so on, okay? And overall now, so this creates my basis set, which is now the sum of all of these wave functions, which I've got right here, okay? So now, in one single observation, one eigenvalue corresponding to psi k at that superposition will be found. Okay? And what that means is, in the case of n equals 1, right, one single observation might mean that, let's see here, it might mean I find the particle right here. Then I do another observation. Perhaps I find the particle right there. And I continue to keep making observations. And if I make a large number of these observations and I average them all together, I will arrive at my superposition. Okay? And so, of course, the more of these wave functions I build in, the more precise my superposition becomes. And so what happens now, the probability of finding that eigenvalue becomes proportional to the normalization constant squared. And now the average of a large number of these observations is given by the expectation value of the operator in question. So what we're doing here now, we're talking about position, okay? So if I wanted to know, a large number of observations, perhaps n is equal to 20, right? What becomes the expectation value of that position? Well, it's where precisely the particle is located, okay? And so once again, right, if I keep adding more wave functions into my basis set, right, my superposition becomes more and more precise. And I can keep cranking this up, right, and you can see just how precise that starts becoming. Okay, it had to calculate, right? It's going to go up to that 1.0 value, right? Okay, so continuing on, what is this expectation value? Okay, so here is, let's see here. Let me get to my cheater notes. Okay, so once again, just in our notation, okay, when we do this symbol right here, that's expectation value of the operator in question, all right? And again, going on this example of maybe just supposing two states, so a superposition of two states, okay? So mathematically speaking, the expectation value will be the square average of those results, okay? Which is given by omega. And so what this means now, this integral here is not unique to quantum mechanics. This is just a mathematical operation to carry out this average, okay? And it's not quite an arithmetic average like a mean, okay? It's an expectation value, which is just another way of doing statistical analysis. And because of this notion of superpositions, right, where we're just adding up a basis set, this is the appropriate statistical analysis on wave functions. Not a mean function, like an arithmetic mean, but rather an expectation value function, okay? So I just want to walk you through what is going on in the math here. So psi n, that corresponds to a normalized wave function. So first the wave function has to be normalized. And we're going to play with this wave function that I've got going on right here. So recall we normalized this last time in our Friday session. And this is actually the wave function for ground state hydrogen atom. Okay, so it's fairly realistic. So psi n is a wave function. Remember, psi star n is the complex conjugate of a normalized wave function. All right. We remember that, so I'll put both of those there. We remember that d tau is r squared sine theta dr d theta d phi. Okay, and so we also remember, just in general, because these are eigenvalue equations, when I take the operator and operate on psi, I get back the eigenvalue multiplied by psi. Okay. So if I continue along here, we know that this is going to equal now psi star n. And so I'll replace this omega psi, uppercase omega. So this is not a W, it's a lowercase omega, lowercase omega, which is the eigenvalue. And we know now that's a real number. Okay. So I can replace that with lowercase omega psi n d tau. All right. And because we know omega is a real number and it's a constant, I can pull that out of the integrand. And so this goes now psi star n psi n d tau. And because these wave functions have been normalized, we know that now psi star psi d tau equals 1, right? And so thus this whole thing just equals omega, the value we want to know, the expectation value, which again, the expectation value is the average of a large number of observations. All right? So let's do a real example. So I'm going to switch over to the Mathematica file, and this is definitely a part of what you're supposed to do in the Math 2 assignment. All right, so I'm going to give away some of the answers, and I'm just going to put that down here below. All right, and so what I also want is my math assistant. So I'm going to use that just to make a nice looking, mathematical operation so we know what's happening. All right, and I'm also going to remind you that I can separate this r squared sine theta dr d theta d phi into its separate integrals. All right, so let's build that up. So I'm going to say, let's see here. I think I can pick that one. Yes, and I'm going to pick this guy. And remember, r goes from 0 to infinity. Okay. So I've already defined my wave function as, let's actually zoom in a little bit. There we go. So I've already defined my wave function as psi. Oops, I'm going to back up because, see, I defined it as psi sub n, so I know it would be, to remind myself that it's normalized. Oops. N, okay. And then bracket r, comma. And let's see, I'm going to put a value in for the bore radius, 52.9, because I want an actual value out of this thing. And of course, I could do this in terms of a, but just to show you that I can get a real number. And I'm even going to go ahead and put this in parentheses just to show you that we can do this as it's properly coded. I'm going to say escape, conj, escape, right? And that gives me psi star. That's going to give me the conjugate. Okay. And so now I'm just going to fill it out exactly like this math says. So if I want to know, for example, the expectation value of position, let me go back to writing over here. Okay. So if I want to know position, I'm just going to say position. That's what I want to know. Then now my expectation value is going to be given by r. And so that means my operator is r hat, and that is just simply equal to r. Okay? So that's all that is. So I'm going to make my operator sandwich. So I'm going to say psi star r. And then now, oops, I'm going to put a space in there just so it knows it's multiplied. And then now escape, oops, let's do that one. Escape psi, escape n. And we know that's as a function of r and the bore radius, 52.9, okay? And so let's see here. So now we've got that as psi, r, psi. And those are all of the dr functions, okay? But remember, I have to have the sine theta, d theta, d phi as well. All right, I can't forget that. So now I'm going to add in my second integral. And just to make sure it knows that these are multiplied, yep, I said space. And then now that's 0 to, I think it's 2 pi. I'm going to double check just so I do this correctly. Oh, 0 to pi. I'm glad I checked. Okay. Escape, pi, escape. And then now that's going to be sine of theta. Okay. Oops. Bracket. And then d theta. Okay. And then now the final integral I need is for d phi. So I'm going to put that in there. And now this one is 0 to 2 pi. So 0 tab 2 space escape pi escape tab. And then now we just know that I'm just going to put it in as 1 because it's just 1 d phi, right? And escape phi escape. Okay, lovely. And so now I've got all of those being multiplied together, and cross your fingers. In principle now, I should be able to hit Let's see here. This one is not doing the color that I want it to do, so let's just see what happens. No, because, okay, so what did you do wrong? So first we're going to piecemeal this thing together. Okay, I'm going to say Control X, and so now if I just integrate that, okay, good, I got a value there. Okay, so here's what we're going to do. I'm going to say parentheses, parentheses, and now I'm going to say that's multiplied by 0 to 2 pi, and then sine theta bracket d theta. Okay, lovely. It took that, so right, it's got the right color there, and I'm just going to put another set of parentheses around that, and then we're going to say space, and then another set of parentheses, and then now 0 to pi, and we're just going to say 1 times, let's see, escape, phi, escape, and then in parentheses, and now, well, I should have gotten a result. So let's say here, evaluate notebook. Oh man, of course it's not working for me. I didn't do. R squared sine theta dr d theta d phi. Jeez Louise. So you know what I forgot? Look, this is great that you're seeing me do this mistake in real time. Okay, so I'm gonna up here, I'm going to remind you, right, that if I have now psi star times r times psi, right, that's my operator sandwich. Psi star r psi. I also have that r squared. So that r squared has got to be there because that's a part of d tau. Aha, so what I need right here is a times r squared, and if we wanted to, because we know that just multiplication by r doesn't change order of operation, so that middle r, I could have called that r cubed. Cross your fingers. Nope, still not happy. So let's see, evaluate quick kernel, local, yeah, do it all up. Okay, let's make sure my wave function looks okay to me up there, right? I defined it as psi r and everything like that. Nope. Well, you guys, you'll have to trust me that it is supposed to work. So let me back out of here and just integrate this part. Okay, so I got a number. Fantastic. So that was supposed to be it. So I wonder if I did make a mistake with this right here. 0 to pi, because I just looked at my notes. Mistake in my notes. I am not editing it out. I'm not going to edit it out so you can see just how I handle mistakes myself. So let's just go back to these notes and let's see what I did here. Where I introduced the spherical chords. Oh, geez, Harmon, here it is. 0 to pi, 0 to 2 pi. So that's what was going on. I forgot the r squared, and I got those mixed up. Okay. I'm glad I recovered that, and I apologize you had to watch me flub around and make mistakes. So going back now and picking up on what the big deal about all of this is and what it means, okay? 79.35 picometer becomes the expectation value. So when we look at psi squared and we find where that value is on this graph, it's not the highest point. That highest point is the most probable, which is a particular type of statistical analysis, right? If we carried out the first derivative on this set equal to 0, we would get that maximum value, okay? But we're not dealing with most probable values oftentimes in quantum mechanics. We're dealing with expectation values because of this whole idea of superpositions. Okay? So 79.35 puts us somewhere about right there on the graph. Okay? And so what that means now, if I was making a large number of observations of this wave function, I'll draw it right here. Okay? That would mean in some observations, we find it right there. In some observations, we find it right there. And we keep going, and we keep going. And if we did this enough times, right, our expectation value would converge to that 79.35. Okay? So let's see here. I've been going about 26 minutes, and I still, I want to just introduce the Heisenberg uncertainty just very briefly. And then on the very last lecture that I record, that I'm going to call Lecture 7B, we'll finish off this discussion of Heisenberg, as well as a notation we're going to use to make our life easier, to keep ourselves from having to write out all of these numbers. So, as a result of all of this stuff, so consequences of superpositions, expectation values, and so on, okay? It is impossible to specify simultaneously with great precision both the position and momentum, which is really to say the velocity of a particle. Quote Werner Heisenberg himself. Okay? So if the position is precisely defined with a large number of superpositions, then all information about the momentum is lost, because any observation of the particle's momentum will be one of the many momentum states used in the superposition. So the way I like to kind of describe what's going on with Heisenberg is if we keep adding more and more and more of these superpositions to get a very precisely defined wave function, we know exactly where the particle is. It's right there. However, we don't know where the particle has been. Think about that for a minute, right? If we know exactly the particle is right there, well, we've added 20 of these momentum states to get to that level, to know that that's where it is with this very tight amount of precision. But because of that, because we've added these 20 plus states, suspect to this large number of averaging, okay, the velocity, in other words, the momentum, so where the particle has been in time, right, we lose tons of accuracy and precision for that case, okay? So the equation for Heisenberg is given by the following. Delta P, so that's the uncertainty in the momentum, and this is not given as final minus initial, rather it's given as an arithmetic uncertainty, okay? So this is the mean square minus the square mean, all square root, which is just a type of uncertainty, like it's a variance, if you will, okay? So Heisenberg says the uncertainty in the momentum multiplied by the uncertainty in the position must be greater than or equal to 1/2 h bar, okay? So for example, if I wanted to know what is the, let me get rid of this thing. If I wanted to know what is the uncertainty in the particle's position right here, well, according to this plot of psi squared, and again, this isn't the same, you know, I'm not getting like a peak from this wave function. And we're going to see that. Sometimes we're going to see wave functions that look like this, that give us this peak, okay? Sometimes we're going to see wave functions that have these exponential decays, all right? So what's the consequence of that? Well, the consequence of this particular wave function, which is actually a realistic one, this is the ground state hydrogen atom. The uncertainty in the position for this wave function is roughly 140 picometers, right? Because it's saying from 0 to 140 picometers, there is finite probability of finding the particle anywhere along this axis. Whereas the expectation value here says it should be about right there. But even so, there's probability finding the particle up here, and there's also probability finding the particle way down there. Okay? So, if in the case for hydrogen, all right, so I'll say in the case of, I'm going to write hydrogen 1s, because that's what we have here. We have the hydrogen atom, the 1s electron. Okay? This delta x is, I'm just going to say roughly 140 picometers as given by our wave function. Okay? Where, of course, now we could use that 79.35 value, right, to calculate that. So that's why I'm just saying it's approximately 140 just by looking at this graph. So now I can calculate what the uncertainty in its momentum is just by simply dividing and doing the algebra. And what's going to happen is, because h bar is like 10 to the minus 34, right? And this number is like 10 to the minus 12, we're going to get a very large value in the momentum uncertainty. And if we were to continue to make that delta x smaller and smaller and smaller and smaller, the delta p would have to get bigger and bigger and bigger and bigger. Okay? So let's see here. I'm at 32 minutes, and I think that's a pretty good place to stop. I'm going to pick up with this more on Heisenberg uncertainty in the next video, as well as Bra-Ket notation. So with the learning goals, okay, so be familiar with the following mathematical operations on wave functions. We've talked about normalization, operators, hermiticity, orthogonality, and now we just talked about superpositions, basis sets, and expectation values. Okay? So in the final video, I'm going to talk more about Heisenberg. So we've talked about the specific form, which is position and momentum specifically. But I'm going to have a little bit more information on the general form. And we're going to use this thing called Bra-Ket. A lot of people like to say bracket, but it's Bra-Ket notation. And that's going to be a type of nomenclature or notation we use to make writing all these mathematical functions a little bit easier. Okay, folks, I'll see you in the next video.